Okay. Hello and welcome to the AP Chemistry Podcast.
Today we're zooming in on the muddy topic of quantum numbers.
First, though, we have to know how we arrived at such. We started with Democritus, who gave name to the smallest indivisible units of matter.
And now we know that even these so-called atoms are divisible under certain conditions.
Yes, and then we moved on to Isaac Newton, who proposed a universe governed by small, solid masses. Next came John Dalton. He also thought that atoms were small. He thought atoms were spherical units with measurable properties of mass. He said that atoms were the fundamentals of the universe. Sir William Crookes discovered cathode rays and found some of their properties. Ernest Rutherford honed the details of nuclear density with his gold foil experiment. H.G.J. Moseley found the charges of these dense nuclei to be positive. Max Planck won a Nobel Prize for the theory on discrete quanta, and Aston discovered the isotopes of atoms with mass spectrography. And finally, we arrived at Schrödinger. He introduced wave mechanics of electrons to the world. He, along with Albert Einstein, Niels Bohr, Louis de Broglie, and Paul M. Dirac, ushered in a new era of quantum mechanics and wave-particle duality. And this led to new models after the Bohr model that explain the dual nature of the electron.
And now we will talk about the quantum numbers we have thanks to all these grades.
So, the first number is the principal quantum number, and that's signified by n up here. This number is an integer that represents the number of electron shells. It starts at 1 and can go up to the outermost shell of the atom, wherever that may be. And that point is always the point where the Coulombic attraction is not strong enough to yield sufficient ionization energy. So essentially, what we have is this. We have our atom, our dense nucleus. And then we have these orbitals, these places where electrons will be located. And they're not always circles, as we'll get to later. But essentially, as the electron moves up in energy level, the ionization energy decreases until eventually you get to a point where there is no ionization energy and the electron will actually leave the atom.
Then we have the second number, which is the azimuthal quantum number, signified by lowercase l. And this number is how they determine the orbital angular momentum and shape of the orbital. The numbers represented are 0, which signifies s, and it's just one circle. Then you have 1, which is p, and it goes like this. And keep in mind these are 3D shapes. Then you have 2, which is going to be d. Then 3, which is f. And f is a bit tricky to draw because it's 3D, but it's something like that.
Okay, and the third number is the magnetic quantum number m of L, and this identifies the orbital in the specific subshell, which are what we talked about up here. The number can be from negative L to positive L, and essentially all this tells you is the XYZ orientation. So the m of L tells you whether this is in the XY, XZ, YZ, XZ plane, or whether this one's in the X plane or the Y plane, and it all depends on the complexity of the orbital. And as you move up, you get more m of L's, so you get more orientations around the atom.
And finally, we're going to have the last quantum number, which is the m of s, the spin of projection. This number is going to be either positive or negative 1/2. And a way to know how this works is to look at electron diagrams. So if you have this, for example, how this end's going up is going to mean that it's got a positive 1/2 spin. In this example, with the same setup, but since this ends down, it's going to be negative 1/2. And that's it for the last quantum.
Okay, so now we have 3 practice problems. So here's the first practice problem. In terms of the principal quantum number, n, how many electrons can be accommodated in a given energy level? That is, in the S, P, D, and F levels. Is it 4n plus 2, 2n squared, 2n, n, or 4n? I'll give you a moment to think about that. And the answer now is 2n squared.
And the explanation is, for any n, the energy level can hold 2n squared electrons, since there are 2 electrons for each orbital.
And then our second question is, what does the azimuthal quantum number reveal about the quantum mechanical model of an atom? The directional spin, the orbital radius, the orbital subshell, the number of valence electrons, or the number of subshells? And the answer, the shape and the number of subshells within the energy level. The explanation is the azimuthal quantum number is the second quantum number designated by the letter L. It gives the shape and number of subshells in a principal energy level, the shell.
Okay, so third question. Which of the following set of quantum numbers is not allowed? So you have 3 sets here, and your answers are all 3 are not allowed, B and C are not allowed, A and B are not allowed, C is the only one that's not allowed, or A is the only one that's not allowed. So I'll give you a second to think about which ones fit the quantum rules. Okay, let's move on to the answer and explanation. So B and C are not allowed, and that's because the quantum numbers, again, they must follow certain rules. So n, the principal quantum number, needs to be a positive integer. So if we take a look at C, we see n is 2.5, so that doesn't work. So we could say C is not going to be allowed. And then we know that L can have any integral value from 0 to n minus 1. So if we look at B, we realize that L is not between the range of 1 and 0. It's 4. And then 3 works out. All the numbers fit their certain specifications. And so that's why the answer is B and C. So now try these worksheet questions, and good luck with your chemistry studying.